Did you want the microphone, or are you okay?
I think I can do it. Okay.
All right, ready?
All right. Hello, everyone. My name is Christine Duval. I come from Clemson University, and I work for Scott Houston. And today I'm going to talk to you a little bit about some of my research. So this project is funded by the Defense Threat Reduction Agency, and they're interested in funding technologies that can be used to combat weapons of mass destruction. So in this project specifically, we're looking at the interdiction of illicit nuclear material through environmental monitoring. So if someone's working with illicit nuclear material and they're assembling a bomb, let's say uranium, there's a high chance and a high probability that they're going to contaminate the environment in some way. Now if we just test the environment and see if there's uranium there, if it's present, that's not enough, because uranium is already naturally occurring. So what we need to do is perform some sort of isotopic analysis. So naturally occurring uranium will be consisting of mostly uranium-238 with a small percentage of uranium-235. Fuel-grade uranium will contain about 3 to 5% uranium-235, but if someone were assembling a bomb, they would be enriching their uranium upwards of 90% in uranium-235, which is the fissile isotope. So currently, there is no fieldable isotopic analysis technique that can be used to fill this need. And what we're limited in is not by the detection method, we're actually limited by the separation materials that are available to do this separation directly from the environment in a fieldable way. So as uranium decays and emits alpha particles, each isotope of uranium has its own distinct energy, and so if we use a silicon detector and we put that near a decaying nucleus, we can detect the alphas and create what we call an alpha energy spectrum. So every time an alpha particle is emitted from your uranium, it hits the detector and it creates a histogram. So the detector recognizes the energy of the alpha and registers one count in the appropriate energy bin. Now the ideal alpha spectrum will produce these beautifully perfect vertical lines, but realistically what happens is there's something that will get in the way of your alpha particle before it hits to the detector, and then you end up with peak tabling. And this can happen if your alpha encounters another uranium atom, if it interacts with the substrate that it's mounted on, or even if it just encounters an air molecule. And so what you want to do in alpha spectroscopy is prepare your samples such that you get these nice defined peaks. Because if you can integrate the peaks, you can know the activity, and eventually you can determine what the intended use of your uranium was based on these mass ratios. So historically, samples have been prepared in a two-step process. So first, you have to purify your uranium and concentrate it from some solution, which is generally your environmental matrix. After it's purified, you have to mount it onto a sample that can go in your detector. The problem with this technique is it takes at least 2 hours to prepare these samples. It can take even longer if your sample is very dilute. And also they require consumable chemicals like solvents for liquid-liquid extraction or strong acids for ion exchange. Additionally, if you're going to do electrodeposition to prepare your sample, you might even need to take an electrolytic cell with you. So if you're thinking about a fieldable technique, these aren't really fitting that need. So what we propose is combining the steps of purification and mounting into one step, and we do that with ultrafiltration membranes. So the chemistry that we choose to use is this ethylene glycol methacrylate phosphate. So this is known to be selective for uranium in environmental waters, and we copolymerize it with a non-binding hydrophilic group. So if we make our water-soluble polymer with a molecular weight that's higher than the molecular weight cutoff of our membrane, we can just filter a simple polymer solution and cast a film on top of our membrane. Then if we flow through our uranium sample, ideally our uranium will be withheld on the membrane, and then there we have our substrate that can go directly in our detector. So we like ultrafiltration because we can do rapid concentration. If you're doing this in the field, you want to do it as fast as possible so we can process high volumes in a low amount of time. We also are minimizing consumable chemicals because this ligand is selective at a pH of 6 directly out of groundwater. And like I said before, we'll mount directly, so this substrate here can go directly in our detector. So in order to test our material, what we do is we put our membrane in a nice ultrafiltration cell. It's plastic and produced by Amazon. And then what we do is we take uranium and spike it in our groundwater. So I want to point out here, it's important to test with groundwater because one of the main known competitors for uranium binding on phosphonic acid ligands is calcium. So here we're working with calcium that's present in a much higher concentration than the uranium. So we flow through our uranium through our cell, we remove our membrane, we put it directly in the counter, and we count for 1 hour. And this is the results that we get. So here we have our alpha spectrum, and what you can see from this natural uranium, which remember was a mixture of 3 isotopes, we have 3 distinct peaks. And so our ultrafiltration alpha spectroscopy substrates are giving us defined enough peaks that we can go ahead and determine the intended use of this uranium that we found. So why is this important? Reducing the nuclear forensics timeline is extremely important if you're trying to catch a terrorist and you want to be able to prevent future attacks. So we think this is a worthy investment because ultrafiltration alpha spectroscopy substrates can reduce sample time, preparation time, avoid the use of consumable chemicals, and you can easily adjust your chemistry to look for other radionuclides. Thank you.
Great. Thank you very much.